Thank you so much. Yeah, I was already introduced, so I can skip that. I have the pleasure to introduce to you our approach on supporting reuse and discovery of ontologies and AEC using modern embedding models. And whoever attended yesterday's committee meeting of the Standards and Modeling Committee already know much of the problem statement, but nevertheless, a short recap. In the last 2 decades, ontologies has attracted a growing research interest in use as well as in development, even though the reuse of ontologies in AEC stays a major challenge, and discovery and alignment are mainly manual in the moment. One of the hindering elements there might be pure documentation and non-human readable specifications, which is suggested. Nevertheless, in the last years, the Built Environment Ontology Lookup Service did a great job in providing an awesome catalog with, I think currently it's 145 ontologies related to the IEC. But nevertheless, the question remains, which one of these 145 do I use for my use case? And with this in mind, we came to a pretty naive underlying question. Can we use modern embedding models to just map the expert suggestion of which ontology to use to the ontologies itself using a shared embedding space? And the underlying hypothesis is basically the embedding hypothesis, which says there might be a shared latent vector space in which semantic relatedness between use cases, ontology, and ontology classes maps to geometric proximity. And from this, we drove basically 3 main hypotheses that we tried to tackle. The first one would be that the similarity in that space aligns with the expert recommendation for ontologies for a specific use case. Like that. The second one would be that related classes sit closer together than unrelated one. So classes that already model a relationship should somehow be close together. And that should also be true for semantically aligned classes. And lastly, we hypothesize that the enrichment with context and structure would support quality in that embeddings. Now, if you want to embed these ontologies with modern embedding models, then at the first moment, we have to define what we actually talking about, what are the entities of interest. Therefore, we defined a data set as a set of ontologies, the ones from the Built Environment Ontology Lookup Service. We said that the elements of interest are basically the ontologies, their classes, and their properties, and that all the entities that might be embedded are the union over these 3 sets. The next step is, because we use text embedding models, in the first step, we need to formalize the representation between our ontology or our entities that we want to embed to a textual representation space. And therefore, we looked in 2 different representation variants. I will come to that in a moment. And then in the next step, you would apply an embedding function that then transforms the textual representation into a latent vector space. We looked in 2 different lexical representations. So the first one would be the representation that takes the direct lexical signal of an entity, which would be the label, the description, and the comments. And then we would have a context-enriched representation that extends this by the direct lexical signal of related objects. Like for an ontology, that would be the main classes of that ontology, extending the direct lexical signal. And then as a baseline, we use a structured representation, which is based on the 2016 RDF2VEC paper, which is an word, basically a back-of-word approach to embed ontologies. That one we used as a baseline. After we formalized what we want actually to embed, the next thing would be formalizing what we mean when we say we have a well-formed embedding space. Therefore, we define 3 geometric criterions on the ontology and the class level, which is on the one hand the global discriminability. So we want our embedding space to have a reasonable distribution of pairwise distances, so no collapse. We want local semantic coherence, which is basically a clusterability test for high dimensions, where you state that k nearest neighbors should have sit much closer together than random pairs. And we would have a non-degenerated dimensionality, where you assume that the embeddings occupy a meaningful manifold of the embedding space. So you neither want just noise, nor you want redundancy. So a meaningful manifold is the goal. And then we use that one as a necessary but not a sufficient criterion, and as a gate to some more semantic criterions. And there on the class level, we define ontology-aware semantic alignment. So classes that already have a concrete semantic alignment in the ontology should be much more close together than unrelated ones. And on the ontology level, external semantic consistency. So the expert relevant ontologies for a given use case should rank among the top k retrieved results in a retrieval task. So in fact, the precision at k and the recall at k should be above a random baseline. That said, we use the data from the ontology lookup service from the 144 accessible ontologies in January. We were able to use 84 because they were resolvable, and they yield enough lexical signals so that it is somehow interesting to embed them. And these 84 ontologies yield 4,166 classes, which is basically the data set that we operate on. For the embedding, we use the Snowflake Arctic Embed 2, which is an open weights embedding model with 1,024 dimensions. And for the RDF2VEC approach, we use the library from the paper with 100 dimensions and a depth of 4 hops and 100 random walks per entity. That said, I would quickly jump to the results. So on the geometric criterions, G1 and G3 were passed by all representations, which is quite nice and states that we have a quite stable embedding space there. G2, so the clusterability basically was passed on the class level, but not on the ontology level. And when we take a closer look to the effective dimensionality, then this is complemented by this because the occupied dimensionality rises from the ontology to the class level. This said, I would move on to the semantic criterions. There on the class level, the ontology-aware semantic alignment was significant for all 3 representations, whereby the structured representation with the RDF2VEC yields the strongest signal, but all of them were clearly significant. Whereby the external semantic consistency, so on the ontology level, we were clearly above the hypergeometrical random baseline, but neither of the 5 cases was significant. So the ontology level embedding alone seems to be not sufficient to reproduce expert judgment. I have to hurry up. Okay, I would quickly revisit the hypothesis. So H1 stays unconfirmed. As we saw earlier, the class level alignment is confirmed for across all classes, which suggests that there could be a reliable approach to support class level alignment. And the hypothesis that enrichment of the representation would support quality is stays unconfirmed, but is still suggested because the structural representation was mainly the strongest. The main limitation is maybe that S2 is clearly statistically underpowered. The expert data set was way too small. Yeah, I leave it with that. Conclusion and future work. Yeah, so the geometric criterions were mainly hit, so that should be a stable and analyze-ready embedding space. The class level alignment was strong. And what is remarkable is that the LLMs using the lexical representation performed quite well without any specific training. For the future work, we would have the robust S2 design, the evaluation of different embedding models, not only one, and the usage of that work to create 2D semantic maps. And after a really, really nice discussion yesterday on the committee meeting here, I used major parts of the night to make these available for you. So the results of our paper, you can now check out in a web app. Try out the vector search with a direct link to the Ontology lookup service, and a 2D and a 3D UMap mapping for the embedding spaces so that you can use them as a semantic map. Thank you so much.
Thank you.